In this video, I'm going to make an introduction to calculus, and I'm going to start by giving one example of application and also by mentioning some historic aspects of the development of modern calculus. And then I will discuss two fundamental problems to our study, which are the slope of the tangent line and also the area of a region. Well, why do we study calculus? A lot of the science and technology that was developed in the last century was possible because of this field of mathematics that we call integral and differential calculus. Just to give you a very present example, here's a picture of the number of cases of COVID-19 as a function of time in the UK. As we're going to see, to determine how fast the number of cases of a disease is growing, we usually use exponential functions as a model because this kind of function, it has a graph that is very, very similar to the one that we see in the picture. Let's say, for example, you were a UK authority looking at this graph in April of last year. Well, maybe you would think that it would take a very long time for the health system to be overwhelmed, which is not the case if we take a look, for example, at November, when the number of cases began to increase very, very rapidly. So if you knew calculus and if you knew that the growth was given by an exponential model, you could take some measures to avoid overwhelming the health system. To give you an idea of the history of modern calculus, here we have the pictures of two mathematicians, Leibniz on the left and Newton on the right. And they were the mathematicians who developed modern calculus in the 17th century in Europe. Even though they worked around the same time, they didn't work together, they worked independently. A fun fact is that calculus was developed during the Great Plague, which happened in the second half of the 17th century. And there was a controversy between those two mathematicians over who developed calculus first. And this happened because Leibniz, he published his work first, but Newton's supporters, they claimed that Leibniz had plagiarized Newton's work. Nowadays, we accept that they both developed their ideas independently. But what really matters to us is that we owe them a lot of the mathematical knowledge that we have today, which has application to different fields. For example, I mentioned an application to biological sciences. The three main objects of studying calculus are derivatives, integrals, and infinite series. Derivatives and definite integrals are going to be introduced in Calculus 1, so in this course, and then they are used in the next calculus courses. But infinite series, they are going to be introduced only in Calculus 2, and they are not going to be part of our course. So briefly speaking, we use derivatives to evaluate rates of change, which is another way of saying that we are interested in evaluating how one quantity changes with respect to another quantity. And we use integrals to evaluate how quantities are accumulated. Another way of putting this is saying that derivatives are related with finding the slope of tangent lines to graphs, and integrals, they are related with finding areas of curves. We're going to take a look at those problems in the next few slides. The first problem that we're going to analyze is the slope of the tangent line. Let's suppose you have a curve of equation y equals f of x and a point P in that curve. Well, how do we find the slope of the tangent line to that curve that passes through the point P? Remember that a tangent line to a curve at a given point is a line that touches the curve only at that point. Well, if the curve is a straight line, we only need an extra point Q in the line. Then let's say that P has coordinates x1, y1, and that Q has coordinates x2, y2. Then the slope of the tangent line is going to be given by the tangent of this angle alpha that I have marked in the picture. And because we have a right triangle in the picture, the tangent of alpha is going to be given by y2 minus y1 over x2 minus x1. It's okay if you don't remember this from trigonometry because we are going to review trigonometry later. Well, what happens if the curve is not a straight line? We have the point P in the curve, but there is not an obvious way to find a second point Q in the line so that we can evaluate the slope. So what we do is the following. We start by taking a point Q in the curve, and this point Q has to be different from the point P. So I want to remind you that the curve is given, so we can take any other point in the curve. So the only information that we have about the red tangent line is the point P. We have no other information about that line. So observe this line that passes through the points P and Q. It's called a secant line. A secant line is a line that intercepts a curve in at least 2 points. And looking at this picture, we can see that this secant line is a very rough approximation to the tangent line. So the slope of the secant line is going to be a very rough approximation to the slope of the tangent line. Now let's consider this second picture where we moved point Q along the curve closer to P. And now the new secant, it gives a better approximation to the tangent line. Well, I think that you already got the idea, but let me show you another approximation that is even better. So the third picture gives an approximation that is even better. So in the third image, the point Q is closer to P. So the slope of the secant line is going to be the best approximation to the slope of the tangent line among those three images that we have in this slide. So we say that if we repeat this procedure to a limit, the secant line actually becomes the tangent line. And in this case, we have the slope that we were looking for initially. So let me show you this in a GIF. Let's do a recap here. So originally we had a green curve and a point P in that curve. Then we took a second point Q in the same green curve. Let's say, for example, that P has coordinates A and F of A, and let's say that Q has coordinates X and F of X. Then moving Q along the green curve is gonna give us better approximations to the slope of the tangent line. I want you to notice that the slope of the secant line in this picture is going to be given by F of X minus F of A over X minus A. So if we move Q along the green curve closer to P, it means that X is actually becoming closer to A. We can say that we can take this process to a limit. And then if we do that, if we take the process to a limit, this is going to give us the slope M that we were looking for, which is the slope of the tangent line. And this is represented by the expression that we have in the slide. We say that M is the limit of that fraction that we have in the slide as X approaches A. And then we can say that the derivative provides us a way to push this process of approximating to the limit to obtain the desired slope of the tangent line. Now let's consider another problem, which is the following. How do we find the area of a region, of a complicated region, using approximations? Well, the ancient Greeks, they knew how to find areas of any polygons. And how did they do that? If we divide any polygon into triangles, as shown in this image, we can simply add the areas of the triangles, and this is going to give us the area of the original polygon. But how do we find, for example, the area of a complicated region? So the Greeks, they used a technique called the method of exhaustion. Let's say that they wanted to find the area of a circle. Then they noticed that if they inscribed a regular triangle in the circle, they would have a rough approximation for the area of the circle. Well, then they noticed that if they inscribed a square in the same circle, they would have a better approximation for the area. And then in general, if we inscribe a regular polygon of n sides in the circle, the approximation is going to be better as n increases. As that means, as we increase the number of sides of the inscribed polygon. And then we can say that repeating this process to a limit is going to give us the area of the circle. Let's say that AN is the area of an inscribed polygon with n sides. Then in this case, we say that the area of the circle is the limit of AN. And then we write this the following way. The area of the circle we represent by A is going to be equal to the limit of AN as n tends to infinity. In chapter 5, we are going to see an idea that is similar to this one. We are going to use an idea that is similar to this one. We are going to use approximation of areas, but instead of using regular polygons, we are going to use rectangles. So like I said, we're going to approximate the area of a region by rectangles. The first picture that we have in the bottom gives us a rough approximation to the area of this complicated region. But if we narrow the base of the rectangles, we are going to obtain better approximations, like we have in the second image, for example. And then once again, if we take this process to a limit, we get the area that we are looking for. And then we say that the definite integral, it provides us a way to push this process of approximating to the limit to obtain the desired area of the region. Well, I have noticed that I'm not very good at ending videos. So from now on, I'm going to finish my presentations as if I were a YouTuber. So don't forget to smash the like button and subscribe. See you next time.